Good afternoon. Today I will talk about the image noise reduction. We know in medical imaging, sometimes because of the image equipment, we cannot get the high quality image. The image you got generally is degraded. So you must do some process to make the quality better. We called this technology to restore the degraded image to a better quality image restoration. In fact, image restoration is different from image enhancement. We will talk about image enhancement in the future. The aim for image enhancement is to make the image visually appear, while restoration essentially inverts the degradation, more objective. In fact, this technology has intersection with signal processing, estimation theory, inverse problem, linear algebra. If you guys want to go deep, you need to learn different courses. But in this course, I don't require you guys use this deep knowledge there. Originally, the image restoration was developed to be used in astronomy, and it's also used for restoring old films and pictures. One important image restoration technology is noise reduction. That's we plan to teach today. This is a medical image. You guys see here the bunch of noise there. So the noise will affect the diagnosis of the doctor. So we hope to remove this kind of noise. In fact, there is a mathematics model for image noise. This just shows the math equation. So this is the image you get through the image equipment. So this is assumed image without noise. If your system is perfect, so there is noise happen, G will equal to F. But for any image equipment, there are always noise happen. So we can express it as this model. Okay, this is the non-noised image. This is the noised image. So N2 is the noise. N1 also is noise. But N2 we called additive noise here. N1 is called multiplicative noise. Why? If you see this equation, this noise just add to the image. Okay, do the addition. But this noise multiply with the image value. So we call this one multiplicative noise. For the additive noise, it's assumed to be uncorrelated with peak values, and it does not depend on spatial coordinates. So that's the additive noise. If you guys learn the statistics theory, then that's very easy to understand here. Okay. For this math model, if you feel difficult, for example, if you have never learned the probability and some statistics, I don't expect you to know this one. Okay. There are different type of noises. There is solid and purple noise. For example, it's showed here. Okay. For this kind of noise, it contains random occurrences of black and white pixels. Okay, that's the solid and purple noise. This one we call impulse noise. It contains random occurrence of white pixels. So you guys see here, there is black point here, also the white point here. But for this noise, just the white points. Okay, so we call this one impulse noise. This one is called solid and purple noise, because the solid and purple, some is black, some is white. Okay, there is one is called Gaussian noise. Okay, the variation of the intensity value, the peak value, will drawn from a Gaussian normal distribution. Again, this is a probability distribution. If you don't understand the probability, I don't expect you to really understand here, okay? Because teach the probability is another math course. So we have three types noise here. We talked just now, this is Gaussian noise. So the distribution of the noise is Gaussian distribution. In fact, based on the noise distribution, we have different noise type. Besides the Gaussian, we have Rayleigh, uniform, exponential noise distribution. So we have four noise distribution here. Okay, but Gaussian is the most popular model because it's presented widely in practice, and also the mathematics is very easy. If you guys know the statistics, a Gauss distribution can be determined by its mean and its variance. Okay, so this shows the shape of the distributions. For the Gaussian distribution is shown here. Okay, then Gaussian have a variance and mean. This is the Rayleigh distribution. This is gamma distribution. This is the exponential distribution. This is the uniform distribution, and this is impulse distribution. We have 6 distribution here that can be used to model the noise. For example, we have a clear picture here. You can add different noise on this picture. In fact, MATLAB provides some function here. Let's see. Okay. See, MATLAB provides this function to add the noise to the image. For example, this is the original image. You can add Gaussian noise to this image. Then you get a new image G. Also, you can add some solid and purple noise on the image. I get the noise image G. Also, you can add another type. Okay. In MATLAB, they did not list all of the noise you can add. Just list some of the noise you can add to the clear image. Okay. In fact, you can write your own code. Okay, to create the noise, then add to the clear image. This one is from the textbook. Okay, this is add Gaussian noise on this image. This is add Rayleigh noise on this image. This is add the gamma noise on this image. Okay. There are a bunch of noise image examples if you found from different field, not just from the medical field. For example, for the thermal image, also there is noise here. Some noise is caused by electrical interference. Some is called the physical interference. For the ultrasound image, you guys already heard the speckle. Speckle is it's sort of image noise. Just now we talk about you have an image. You can use MATLAB to add different type of noise on this image. If you already have this kind of image, how to know the image is a Gaussian noise, or is a Rayleigh noise, or is a gamma noise? Another important thing is for your image system. Okay, for example, you have an ultrasound image system. You get the image. How do you know the noise is Gaussian type or is other type of noise? Also, you have CT. Okay, how to find the distribution of the noise? It's Gaussian distribution, it's a Rayleigh distribution, or it's a uniform distribution. How to do that? The simple way is like this one. If you have an image system, for example, you have ultrasound image system, okay? You can use Phantom. Phantom is a uniform background, okay? It's a uniform background. So you can image the uniform background, okay? Then you get that image. If you get that image, then you can based on that image to find the type of the noise. How to find the distribution of the noise? We can calculate its histogram. Okay? Let's first explain what are image histograms. Okay? For example, you have an image here. Okay? That's the image. We say this is the 1, 2, 3, 4, 5, 6. It's a 6 by 6 image. Okay? Because it's a 6 by 6 matrix. So an image histogram is a plot of the gray level frequency, okay, which means the number of pixels in the image that have that gray level. For example, you have image here. We have different gray value, 0, 2, 7, 1. Okay, you want to know how many zeros in this image, how many 2 in this image, how many 7 in this image. Okay, then you get the frequency f0 equal to 18. That means there are 18 0 in this image. Then f1 equal to 6. The pixel value is 1. F is frequency. That means there are 6 1 in this image. If you count 1 1, 2 1, 3 1, 4 1, 5 1, 6 1. So the frequency is 6. Also, how many 2 here? You also count 1 2, 2 2. So f2 equal to 2. For the 3 4 5 6, that's 0. Okay, f7 equal to 10. That means there are 10 7 in this image. So you get the frequency of these pixel values. Okay, then you draw the figure. Okay, for example, 1 happen 6 times, 0 happen 18 times. Okay, 3 happen 0 times, 4 happen 0 times, 5 happen 0 times, 6 happen 0 times, 7 happen 10 times. Okay, then you get the histogram. Okay, so from the histogram we can get the probabilities, because we totally have 36 pixels, because the image is 6 by 6. So if we divide the frequency by 36, okay, then we can get the probability of each pixel happen, okay. P0 equal to F0 divided by 36, then we get the 0.5, okay. P1 we just compute, get 1/6. Then for the probability of the pixel value 2 happen, we'll get this one. It's 1/18, okay. For the pixel value 3, 4, 5, and 6, the probability is 0, okay. So in fact, this is a very simple concept shown here. In fact, these probabilities estimated by this formula we called normalized histogram values. It's corresponding to the value here, because this is just frequency, okay. We do some normalization, means we divide by m, so we called this kind of probabilities, we also call them normalized histogram values. Then when you draw a graph, then we call this graph is normalized histogram. So the x coordinates still great value, okay. The y coordinates means the estimated probabilities. For example, for the pixel value 0, the probability is 0.5, okay. For the pixel value 1, the probability is 1/6. For the pixel value 2, the probability is 1/18. For pixel value 3, 4, 5, 6 is 0. Then for the pixel value 7, the probability is 5/18. So we call this one is a normalized histogram. So this is show the histogram of a real image, okay. Because I use MATLAB they just collect the values, use a line, okay. So not like here, they not collect. For example, in MATLAB they will collect this point, and this point, this point, this point, this point, this point, and this point. So that's shown in the MATLAB. So now let's talk about how to identify the noise type. For example, we have an image here. You want to know what type of noise in this image. In order to identify the noise, first you need to select a uniform region in the image. Generally, the pixel value in this area should be not close to 0 or not should be white area. After that, you will compute the histogram in this small area. Then you estimate the probabilities of the pixel value in this region. Then you plot the probabilities and see the shape. Based on the shape, you can find the noise type. However, if you want to get the exactly noise distribution, include the parameters in the distribution, you need to use some mathematics to do that. But that will be beyond this course. This is the MATLAB code to estimate the noise type. I will use the example to show how we to do that. If you see this code, first we get the image, okay? Read the image in the matrix A, then show the image. I put hold on here. That means when you show the image will be there. Then you can add another themes on the image. Okay. Then we get the small area. We get the left top points and the right bottom points. Then you get the coordinates of the small region. In fact, these themes we already done before. Okay, let's get the pen. Also, we introduce another function here. Okay, this function, in fact, is draw a rectangle on the image. The position here is just you don't care about. Okay, you just put here. Then you put the coordinates of the start points of the rectangle. For example, okay, the start point is here, so it's x1 and y1. That's the start points of the rectangle. Okay, this point. Then you put the white. Okay, the white is from here to here. That means this is white. Then you put the height of the rectangle. Okay, will be y2 minus y1. So this is the height. After that, for this kind of edge, you need the color. Okay, when you show the rectangle. So I put the color. If you put a G here, that's green. If we put the R here, it's red. If we put a B here, it's blue. Then also the sides of the line, okay, called the line wise. I put 3 here. So let's first show them in the MATLAB one by one. First we read the image. Okay, this we have done before. You can just copy here. Okay, let's see. This is show the image. Okay, so next step is just select the small region. We already talked about how to select the small region in our previous lectures. First, you get the point on the left top, then get the right bottom points, then you get rectangle. Okay, so we use these 3 themes to do that. Okay, you get the left top point, then get the right bottom point. After you get the left point and the right bottom point here. Okay, let's get the pen to see. So this is x1, y1. This point will be x2, y2. Okay, that's we get the 2 points. X is the x coordinates. Okay, y is the y coordinates. That's you need to know. Okay, x, y. So x2 minus x1 will be the width. y2 minus y1 will the height. Okay, so first we get the x, y. Okay, then we draw this rectangle on the figure. We need to draw. Okay, let's draw up. We run these sentences. Okay, let's see what's happening. See guys here, that's the rectangle sentences do. Okay, they will draw the region, use the rectangle we get. Okay, that means the noise estimation will be done in this small area. If you guys really want to learn how to use the rectangle, also I suggest go to MATLAB website. They are there, okay? For example, you can find on the MATLAB website. I'm sorry, MATLAB. Then see here, okay? Then the bunch of use of them, okay? They will show the example how to use it, okay? So after you draw a small area, okay, then we compute the histogram in this area, okay? First we need the sub-image for this area. Get a sub-image, we also know how to do in the past teaching, okay? You can use this one, use B, okay? The sub-image is from Y1 to Y2, the X is from X1 to X2, then you get the sub-image B. After you get the sub-image B, then we can use the themes we teach here, okay? First get the histogram. In MATLAB, they already have the function there to get the histogram, okay? Let's get the frequency, okay? Use the image histogram B, okay? Just run this one. Okay, you get count. Counter is the frequency of the pixel value corresponding to 0 to 255. So if you type the count here, see, also you can count it as a low vector, okay? So you guys see here, totally there is a 256, because for the image, the value is from 0 to 255. So we totally have 256 pixel values. So showed here, the first is the frequency of pixel value 0. The second one is the frequency of the pixel value 1. The third is the frequency of pixel value 2, okay? So you can get all of the frequency of the pixel values from 0 to 255. How to plot the histogram? One thing you can use, create the pixel value first, okay? For example, you create t equal to 0 to 255, okay? That's t. Then you plot, you can put a figure 2 here, okay? Figure 2, show in the figure 2, plot t and count. I'm sorry, there is an issue here. Oh, no, there is no x, it's t, okay? See, that's the histogram. See the pixel value from 0 to 256, okay? 255. Then this is the frequency. This is the histogram of the image. So also we can get the normalized histogram. So we need to estimate the probabilities of each pixel, okay? That's much easy, okay? You just need to divide the count frequency by the total number of pixels. The total number of pixels can be obtained by sum of the frequency, okay? Then you use this one to get the property, okay? That's P, okay? The same, you can show the normalized histogram on figure 3, okay? T, then this should be P, okay? See here, that's the normalized histogram. If you guys compare this figure 1 and figure 2, the shape, they're the same. The only difference lies on the y coordinates. This is the probabilities. This is the frequency. Okay? Frequency here means the number of the peaks values. This is the percentage. You can say it's the percentage of the peaks values. Okay? This is 30. This the maximum value is 30. This is 0.025. Okay? But the shape is the same. Okay? So in fact, also you can show the image B. You can, for example, you don't show as figure 2 because figure 2 we already show the histogram. So you can show on. I'm sorry, I show figure 2. You can show figure 4. Okay, figure 2 is still show the histogram. Okay, figure 4 is the small region, so you still can show the figure 2 as this one. Okay, so we have figure 1 is the original image. Okay, figure 2 is a histogram of the small area. Then figure 3 is a normalized histogram. Then figure 4 show the small area here. Okay, so that's the things show how to estimate the noise type. So based on these two figures, do you guys guess what type of noise here? If you guys go to here, okay, you guys can compare this shape with the noise types distribution here. You will find that this shape is similar to the first one. The first one is the Gaussian noise. So the noise type in this image is Gaussian. Okay? For Gaussian noise, in fact, you can use the mean and the variance to get the exactly distribution. Okay? How to compute the mean and the variance? If you guys already learned the statistics, you will know. For example, Zi is the peaks value, P is the probability of Zi. Then you multiply them together. Okay? Then add all of these peaks value together, then you get the mean. The variance can be computed in the same way. In fact, I also try some other images. Okay, estimate the noise. There are 3 types of noise on the image. One is, see this shape, it looks like Gaussian, but for this shape, it looks like really distribution. For this one, it looks like a uniform distribution. Okay, so based on the method we talked here, you can estimate the noise type. After you estimate the noise type, then you can develop some technology to remove the noise.